Okay, so going back to what machine learning is, we've talked about these kinds of functions that we're trying to model. We've talked about linear functions in particular, but we eventually want to build more complicated models. So before we get to the model building, we have to talk a little bit about the data that we get from the real world. In general, that data can come in continuous format, for example, the temperature or some time or distance, or it can be categorical data, so discrete data, like the day of the week, or a car model, or the flower species. And to make the categorical data easy to deal with, you often need to encode it into a continuous type of setting. So this is called one-hot encoding, and this is just one way to perform this kind of conversion from categorical into continuous. And the reason this is important is because of the calculus part of this discussion. We need continuous differentiable functions, and those need to be functions from like a continuous space to another continuous space. So we can't really deal with categorical data directly when you're using these kinds of continuous models. So we have to perform this one-hot encoding. And it's really simple in terms of the idea. If you have n categories, you just take a vector with n entries. And for each category, you're going to assign the ith category as the ith entry. Right? So if I have, for example, Monday, or a day of the week, I can encode it as this 1 followed by 6 other zeros. You're free to choose like the order. Like you could switch the encoding for Tuesday and Monday. It doesn't really matter, because in the end we're going to be training the model. But this just makes sense here. So I want you to write a function which performs this one-hot encoding. So here I have a list. And what I want you to use is this other keyword I haven't introduced, enumerate. And what it does is it tells you to take the list and to return both the index and the element of the list. So we're iterating through this list in terms of its index and its day. So in particular, if you print out this dictionary, you'll see that Monday goes to 0, Tuesday goes to 1, etc. So this is a bit of a harder coding exercise, so I'll get you started. Let's say our encoding. So what this does is it creates an array of zeros with 7 entries. So I want you to put something here that returns the correct encoding given this dictionary. So any ideas what we should be putting on this line? So this dictionary tells you what index we should be setting to 1, right? So let's say index is dictionary on the day. And then here, we would set that index to 1. So let's actually print out the one-hot encoding for the day, for day in test days. Oh, sorry. What? I have to run this first. Oh, I also forgot to run. I forgot to add this stuff. All right, so you'll see we encoded Monday into this 1 with zeros. Thursday, the 1 is in the 4th entry. Tuesday, you have 2 Tuesdays here, just like in this list. And then Sunday is here. Okay. Another essential skill is reading in data from files. So in Python, there's one way to read in files. So I want you to write or run this cell first. So what this does is it just writes this data into a file in your current Colab session. And then here I actually want you to read the file. So I want you to replace the none here using this line.split option or function to split each of the lines in the file by the comma. So I'll just do this quickly. And you can see that what we've done is we've read in the file. This creates an iterator over all of the lines in the file. And for each line, we've split the line on this comma. So if you can see what we wrote into the file, we wrote student ID and grade. And then for the rest, we have the ID as an integer and the grade as an integer. Except that when you read in characters like this, Python assumes they're strings. So I think we have time to do this challenge exercise. So now that I've already taken care of this for you, I want you to convert each of the strings that was in this list into integers. So using this list comprehension. I'll give you a minute to think about that. So for each of these tuples in the list, we're skipping the first line because that was just the headings. We're going to return a tuple, and the tuple is going to have the student ID and the grade. And you can see instead of these strings here, instead of these strings here, we have normal integers. Fortunately, most of the time you won't have to do any of this data wrangling. Pandas is a package that helps you deal with all of this. So here I've used this function from Pandas called readCSV, and it does exactly what you expect. And it even formats the entries into a nice table. So for example, if you get just the column with the student IDs or the grade, you can see they're the correct type. They're already integers. So Pandas tries to make things easy on the user. This first column is just like the row index. And notice here, because of the way I actually wrote this file, there's actually a space here before grade. So that actually becomes part of the column name, the space. But you can see we can index into the columns with these square brackets. So grades is this data frame, and we're indexing into it. To kind of correct this mistake, I don't really want a space here. You can either edit the file, or you can create a new column here without the space. So if I print grades here, oh. You see initially we have two columns named grade, but one of them has an invisible space here. But then we're going to drop that invisible space. So then you only end up with this. And then you can write this. Oh, right. So unfortunately, I already overwrote grades once, so it didn't have this space. But now you can see that we can index without the space in front. OK, so this is a short exercise. Using these functions from NumPy, find the mean, median, and standard deviation for the grades. So since we've imported these functions by name, we don't really need to write np.mean. But I'm going to grab all the grades, and then I'm just going to call each of these functions separately on that list of grades. OK. OK, with that out of the way, we can talk about neural networks, the motivation, and how do we work with them. So biological neurons are systems of cells that fire electrical impulses to each other. And each neuron typically has like 10,000 inputs from other neurons. And it can also project 10,000 outputs. So neural networks, artificial neural networks, are inspired by these biological neural networks because of how well neurons perform and how efficient they are. And the way it's modeled is that, for example, you might have two inputs. Say these are your eyes, and the retina sends axons to the visual cortex, which are these blue circles. And these blue circles each represent a single neuron, which takes in the inputs, so the two inputs, does something to that data and then fires an output. And so in the integrate and fire model of neurons, what these neurons are doing in your visual cortex is taking the data that's input, summing them in some way with specific weights, and then determining an output based on that sum. And if you think of it mathematically, what you're actually doing is you're taking some combination of the inputs as your intermediate representation in the visual cortex. So this is an expression of that combination. So let's say your H are your inputs. Your H prime are the outputs of your visual cortex. And then you can phrase this as a matrix multiplication. So each of these neurons, their outputs are determined by a linear combination of the inputs. And to model a little bit of the non-linearity of neurons, so they don't just straight up sum the inputs, they perform some non-linear thing on them. We use an activation function. So that's here. And the activation function is just a way to introduce non-linearity into this kind of matrix multiplication problem. So mathematically, what deep neural networks look like is you'll have lots of these hidden layers which linearly combine their inputs, non-linearly activate the output, and then pass it on to the next layer. So it'll look like a really long list of functions applied to the inputs. And in the early 90s, I think the earliest paper was in 1989, it was shown mathematically that if you have enough neurons, you can always approximate any function, any continuous function between any kind of real continuous inputs and outputs. But the aim of modern machine learning and neural networks is to decrease the number of connections that we need to make and to try to understand why certain architectures for neural networks work better than others. Okay, so just as a first example of a deep neural network, I'll have you run this cell and then also this cell. And this is just the simplest kind of model you can make in PyTorch or TensorFlow. It's a sequential model. So it looks a lot like what we have here, where we have one input. We have a hidden layer with 128 neurons, and we have an activation function. And you can see I just repeat this a few times. So in this layer represents basically a 1 by 128 matrix multiplication, or a matrix that stores weights. This one is 128 by 128, and then this is 128 by 1. So in this problem, I'm just going to use a simple exercise, which is let's fit sine of x with a neural network. So it's going to take one input, which is the value of x, and try to predict an output, which is sine of x. So if you use this model and you use this automatic differentiation framework we've talked about, you can train this for a few thousand iterations. And there's a lot of different algorithms for training, but the one that is kind of the gold standard now is this atom optimizer. So we've performed the training. It's super fast because it's a pretty small model. And now we just, you have to do all of these operations. But eventually you can plot. So the ground truth, that means are what we're trying to predict, which is sine of x. That's the orange. And the trained model prediction is the blue. So you can see just from this small example, we've taken linear transformations and just these nonlinear activation functions, And we're able to approximate the sine function to a very high degree of accuracy. And so the standard introduction to machine learning is this MNIST digit recognition task. So the idea is you have handwritten digits, and each of them is a specific number, and the goal is to predict which number you have from the image. So this cell just helps you get all the data in the correct format. We'll work through how you get data in this format tomorrow during the, I think it's an afternoon session. So you can run this cell, and what you can see is that there are 60,000 images in the training data set, and there's 10,000 images in the test data set, and they all look kind of like this. They're 28 by 28 black and white pictures. And so instead of just a linear layer like I showed before, we're going to have convolutional layers. And I'll talk about this in a little bit. But it's pretty much the same kind of model where we have a convolutional layer followed by an activation function. And we kind of repeat this a few times. We also throw in some linear layers here. And you can see when you have a more complicated model, you have to actually write it in this format. You can basically copy and paste this kind of format to create your own custom model. But the important thing is you need to first store all of your layers using this self dot function. So this stores this layer as self.conv1. And then you need to implement this forward function, which takes self and then your input. So you can see we can access all the layers that we've stored in this model here in the forward function. And so what we're doing here is we're taking x, we're convolving it, activating it, convolving, activating, and reshaping, and then passing through some linear layers. And so it's named forward because you can take the backward easily. The backward is, you don't have to define the backward because automatic differentiation does that for you. OK, so I'll do that. You can also speed the model up a little bit with this torch.script. We'll use the Atom optimizer. And we'll use this data loader to kind of break up the 60,000 input images into manageable pieces, chunks, for the model to train on. And yeah, we'll just train it. It's typically very fast, especially if you have a GPU. So we'll just wait for that to train. And the nice thing is that this would take, if you tried to do this by hand, if you tried to do all these matrix multiplications by hand, it would take you forever. Computers are super fast. The clock speeds that they quote are how many mathematical operations they do in a second. So if you have a 2 gigahertz processor, it does 2 billion operations a second. So yeah, this is almost done. And these kinds of models often outperform humans. For example, you'll see the training accuracy in a short while, that we get almost like 97, 98% training accuracy. And the reason we have to split this data into training and test sets is because we want to make sure that the model can generalize so that we're not just overfitting on the training set. So here we got an accuracy of 97% roughly, and 97% for the test as well. And why isn't this 100%? Well, some of the digits look like this. Like some people have really awful handwriting. So I don't know what this is. This could be a 6 or maybe a 4. This could be a 3 or an 8. So there's specific cases you're not going to get to 100% just because of noise in the training data. Okay, so this is a nice application of neural networks in the field of computer vision. And there's all these different architectures that you can read about that have been proposed. You know, it just goes on and on. And the basis of each of these architectures is you're still using linear algebra in some way. You're still using activation functions in some way. But it's how we reduce the number of parameters that we have to train. So, for example, ChatGPT, like all of those AI chatbots, they use attention, and I think Jen will talk about that more tomorrow. Generative adversarial networks is essentially two networks. Here's one network and here's another. One network is responsible for generating fake images or fake data, and the other network tries to determine if it's fake or real. So the generator and the discriminator. And before diffusion models, this was like the state of the art in fake image generation. Okay, so I'll talk briefly about convolutions so that we can understand what convolutions are. We'll start with one dimension. So typically you want to use a convolutional layer when you have sort of spatially organized or temporally organized data. So for example, if we have an audio recording, we might record like over 40,000 times a second the volume of each of the microphones. So, well, maybe we have some additional data here too. So we have two pieces of data that we're recording, V and F. They're kind of associated to each other, right? So that we want them to be considered together when we're processing the input. And then a convolutional filter kind of passes over the entire sequence and takes small groups of data and looks at those together. So in this case, if we have a kernel size of 3, so that just controls how big a window we're looking at, we might take these first 3 elements of the sequence and do something to this. For 2D convolutions, these are really well suited for images. You'll have a kernel here. You can see it in the bottom right corner. We're using the same kernel on every 3x3 subset of these pixels, and we're computing some kind of value out of here. And this is actually very much what the human visual system does. Like it's known from experiments that the human visual system has these filters in the form of the retinal ganglion cells and bipolar cells and all of this processing in your visual cortex. And that's kind of the inspiration for these convolutional neural networks. It's really efficient for image recognition both in animals and computationally. So this is kind of a representation of some of what are called receptive fields, or you can think of them just as the convolutional filter weights that you might have. So for example, this kind of filter would detect whether you have a line that's oriented in this direction. And so you can see there's a lot of these filters that were trained in this in an artificial neural network, which deal with the orientation of lines. There's other ones for color, for example, and it's really interesting. I think there's also this really scary application of filters, which is these eigenfaces, where you're characterizing faces by how well they line with each of these filters. But yeah, computer vision, I think when they originally, computer vision started as like a summer project for a grad student in CS, and the advisor was like, oh, you just need a summer to solve this field, and 50 years later, we're still trying to figure out how to process image data. Okay, so that's like a really quick overview for what neural networks are and kind of the rationale behind them. We will go through this this notebook tomorrow, and we're going to take data from this publication from, I think, the 70s, where they recorded all of these different aspects or characteristics of abalones, and they also recorded the age. So we're going to be predicting the age from all of these characteristics. You can take a look at that now, or we'll go over it tomorrow, but there's a lot of exercises here that we'll go through. All right. And with that, that's the end of our morning sessions. Thank you for coming.